Okay, off we go. So I want to finish up on coercion. That'll be the first couple of minutes, not too long. And then we'll talk about attributes and how attributes build off of atomic vectors to create other data types. And then we'll talk a little bit about missing values. That'll be pretty brief, but I just want to talk about essentially how missing values can create more missing values and some ways around that, okay? Then we'll have an intro to lists. That'll be the last third or so of the lecture. And we'll talk specifically about subsetting lists versus atomic vectors and things like that, okay? So the main learning objectives for today are to understand the fundamental differences between lists and atomic vectors. I don't think I mentioned this before, but atomic vectors are called atomic vectors because they are literally like the atoms of R. So they're small pieces that build off of, build on top of each other with these different attributes and things to create all of the other different types of data that we have in R. We're also going to talk about coercion, as we already did, but we'll finish up on that. And then various ways to subset vectors. So how do you get a specific slice of the vector out, whether it's a list or an atomic vector, because those are going to be different, right? And then understand what an attribute is and how to set and modify attributes generally. Okay, so we're not going to go in breakout rooms or anything. But I'm just going to start the timer here without actually running the code. Take 1 minute and predict what do you think each of these vectors will end up being coerced to. Okay? So just think through it, maybe write it down on your screen or elsewhere. Okay, so first one, true, 1L, 0L, false, but in quotes. What do you think that one's going to coerce to? Somebody volunteer, please.
String?
String, correct. Character. And why is that?
Isn't that I forget what the exact term is, but it's the lowest common denominator. Like if
Yes.
there's everything else, if it's strings in there, it's going to be a character.
Yes. So that is correct. So it's the most flexible type, right? Good. What about this second one, 1L and false?
Integer.
Integer is correct. And what specifically will the integers be?
It'll be a 1 and a 0.
That's correct. Yes. So trues and falses get coerced to integers or doubles, and the falses turn to zeros and the trues turn to 1. So that's why you can do things like figure out how much missing data there is pretty quickly by summing a logical that asks if the data are missing or not. Okay. Third one, 7L, 6.23, and 8 in quotes. Somebody else?
Character.
Character, again, because we have a character in there, so that's what it's going to coerce to. Pretty simple. If there's a string in there, that's what it's going to coerce to. All right, and then the last one, 1.25, true, and 4L.
Double?
Double is correct. And the reason is because double is more flexible than integer, which is more flexible than logical, right? So you can keep all of the information that you have in this vector through type double, but you can't through type integer or type logical. Either of those you would lose information, right? Good. Okay, so here are the answers. We just use type of. So type of on the first one, we get character. Type of on the second one, we get integer. Type of on the third, we get character. And type of on the last one, we get double. So we were right on all of those. Okay, now I am going to put you in breakout groups. And what I would like you to do is basically, we probably won't actually spend 8 minutes on this. That's kind of a long time, but maybe 5 minutes or something like that. What I'd like you to do is create, just have one of you screen share. This works better if we're in person, but we're going to try anyway. Okay, we're going to have one of you screen share and create 4 atomic vectors, one for each of the fundamental types. Okay, so create 1 character, 1 logical, 1 integer, and 1 double. Okay, then you're going to take turns basically combining them. So like only one of you is going to screen share, right? But the first person would combine, say, double and integer, and then they would say, okay, so what's this going to coerce to, right? And basically you're just going to quiz each other. So then the second person would say, okay, what if we did, you know, integer and logical? What would that coerce to, or whatever? Okay, so you're basically just going to quiz each other. Probably not 8 minutes, like I said, probably more like 5 minutes. Basically, what I'm trying to get at is that this or hopefully this will start to feel natural to you, and you'll start to get fluent with it, because as I sort of mentioned last class, this is often where errors can come from, because you're doing something and expecting some sort of output, but you're getting a different kind of output. And it's often because some sort of implicit coercion is occurring. And even when you're trying to do explicit coercion, as we talked about last time, the implicit coercion happens first, usually. So there's ways around that, right? You can basically break up the vector, if possible, coerce each element or each part of the vector, and then put them all together, or something like that. But it's a very regular source of bugs in code is coercion. All right. Questions on that at all? Or how are we feeling on this? Give me like a thumbs up, thumbs down, whatever. Okay, good. Okay, so we're going to move on to attributes. Hang on just 1 second. All right, so what are attributes? Attributes are just metadata. So what's metadata? It is data about the data, okay? So you have some data, like a vector, right? And then it's data about that vector, all right? So this is how most other data types, in fact, I think basically all, are created, either through attributes with atomic vectors, or through the combination of lists and atomic vectors with various attributes, okay? So what are some other data types in R? We've only talked about atomic vectors really at this point. Of course, we know we have data frames, we have matrices and arrays, we have factors, we have dates, etc. Okay, and this is because, like I said before, atomic vectors are the atoms of R, right? So that they're very small in that sense, and everything builds on top of those to create these more complex structures that can do a lot of different things. Okay, so some really common attributes that we have, for most objects really, is names, right? Names are super common, but even there we don't always have them, right? But we very regularly have names for vectors or for whatever. We also have dimensions fairly commonly, right? Like a 3x2 matrix or whatever. Less common, there's actually endless arbitrary metadata that you could add to any object. And that's a way that you can sort of just store information about something and sort of hold it there as you go along in your process. That's not something I would generally recommend you do. And we'll talk about this more later, but the main reason is because many operations will actually strip attributes from the object. And so if you have some arbitrary metadata and then you do some, like maybe you compute the sum of that vector, you may lose that metadata in the process, okay? You might lose those attributes. So here's some examples. Please follow along. I'll give you a minute here If you don't already have it installed, please install the Palmer Penguins dataset. That's all it is a dataset. But install .packages Palmer Penguins, and then just go ahead and say attributes on Palmer Penguins. I've limited this to the first 50 rows. That's just because I wanted to keep it all readable on the slides. Okay, so you could do it on the entire data frame. Give you 1 minute to get set up there. Give me a thumbs up when you're ready, please. Good, that looks like most people. Just a few more seconds here. All right, so what we're doing here, after I load Palmer Penguins, I'm using attributes, right, which is a function, to list all the attributes of that object. Okay, so I'm being purposeful when I'm saying this because there's sort of two different functions related to attributes. This one is only for listing attributes. Okay, so I'm not actually doing anything to the attributes here. I'm just listing them. All right, so this data frame has 3 attributes: names, row.names, and class. Okay, and each of these attributes are atomic vectors, right? So the names attribute is an atomic vector, which are the names of the columns of the data frame, right? So this is a character vector. The row names are it's just a numeric row number, right? 1 to n, and that's going to be an integer vector, right? And then finally the class, which is also a character vector, but because this is a tibble, it has 3 classes, okay? So it's going to basically try to use tibble.df. If that doesn't work, it's going to try tibble. If that doesn't work, it'll fall back on data.frame, okay? And essentially, this is just like, if you don't have tibble installed on your computer, then it's going to act and be a regular data frame. Otherwise, it'll act like a tibble, okay? So these are the attributes of this data frame. When we look at the actual object, we can see it just looks like a normal data frame, of course, right? But right here, right, this is the names, not column names, right? And I'll mention why later, but that's the names. And then here's the row names. And we can't really see the class of the object here, but we can see the names and the row names. Okay, let's say we wanted to get a specific attribute, okay? There are very regularly ways to get attributes without actually using the attr function, but that's the most general. So that's why I'm using it here, okay? Specifically because we're talking about attributes as well. So attr is obviously an abbreviation for attributes, and this is the second attribute function that you can use to actually access the attributes of an object, okay? So I used attributes back here to list the attributes. Now I know I have names, row.names, and class. So if I want to access one of those, I use attr on that object and then just list the attribute I want to access from there, okay? So this is getting the class attribute out of penguins. This is getting the names attribute out of penguins, okay? Note, as I mentioned just a second ago, this is not generally how you would do this, right? Very regularly, there are functions that have been built for you to access those attributes in an easier way. And beyond just being easier, they often are better. And so for example, coef, right? COEF. That's a function to extract coefficients from model objects. And for most model objects, that's going to be the same whether you dig into the list of the model object and pull out the coefficients, or if you use that coef function. But that's not always the case. Sometimes when you use coef, it's actually going to do a few additional calculations to the coefficients to make them on the scale that you expect them to be, or whatever. So the coef function is not only an easier way to get the coefficients, it's actually safer because the developer has built it for you in a way that you're getting back the coefficients that you would expect. All right. So whenever possible, these are actually how you would want to access these things, is with these sort of helper functions. But this is the more general way that you can access any attribute within any object that has attributes. Okay. You also want to make sure that you're specific. So on the last slide, right, I'm asking for attributes of the data frame. But is that always what I want? Maybe. I don't know. I don't know what I'm trying to do, right? I'm just talking about attributes. That's all I'm trying to do. But sometimes, right, I might want to access the attributes of a column in the data frame. All right. So specifically, if I look at like the species column in penguins, you'll see that it has two attributes, levels and class. Okay. That's because this is a factor. And so you can see the levels here and the class here. Okay. If I call attributes on a different column, like bill length, I get null, because that column is just a numeric vector that has no attributes. Okay? So this is just to say, make sure when you're calling attributes that you call the specific thing that you're interested in. Okay? You can also redefine the attributes with ATTR. Okay? So here I have penguin species. I'm using ATTR, and I'm saying, give me the levels attribute. Then I'm redefining them over here. I'm calling them big one, little one, funny one. All right. And then when I look at penguins, you can see species here now says big one a bunch of times. Right. And when we get to the other ones, it would say little one and funny one. Okay. Again, this is not generally how we would change the levels of a factor. We wouldn't use ATTR. We would use the levels function and then redefine it that way. Okay. But this is the most general way to access attributes. Yep. Meg?
Sorry, that on that previous slide, so you replace them with levels, but how does it know which one to give which level to, or is it kind of arbitrary?
No, it's not arbitrary. Good question. So back here, when I called attributes of penguin species, we can see it has a levels attribute, and that those levels are Adelie, Chinstrap, and Gentoo. All I'm doing is redefining these big one, little one, small one. So Adelie becomes big one, Chinstrap becomes little one, and Gentoo becomes funny one.
Okay, thank you.
Yep. Other questions?
Daniel, I have a question.
Yep.
So if you had 10 or 20 different relabels that you wanted to do, is there a faster way to do this? Could you load a data file and have that replace it? Because you wouldn't want to type out every single one.
Yeah, so if you have a bunch of things that you're redefining, like in levels or whatever, you however you want to get that vector that you redefine, you could just basically store it into an object and then say levels of this thing is this object. Does that make sense? There's also,
yeah, it does.
The forcat package for factors generally will help you with a lot of that kind of stuff. Any other questions?
What if we only want to change, let's say, 1 or 2 levels, but let the other remain the same?
Mm-hmm. So in that case, like let's say I wanted to redefine the first 2 here, right? What I would need to probably do is actually subset this right here So it's only returning the first 2 levels. So I would write this, but then I would have a square bracket here where I would say 1:2. And then over here, I would just define it as big one and little one and leave out funny one. Does that make sense? And then that would overwrite these first 2, but it would leave the third one because the only thing I'm redefining are these first 2. But again, probably wouldn't use ATTR. We would just use the levels function. Other questions? Okay, so let's talk about dimensions now. Dimensions are another really common attribute, right? And they come from matrices and arrays, right? So please do this with me again. Let's create a matrix. We'll call it M that goes 1 to 6, and we're just saying n call equals 2. So a matrix that has 2 columns and has the values 1 to 6. And if you're done, you can watch my cat going crazy in the background. He's good entertainment. On cue. All right, so I want to point out how this matrix fills too, right? It fills by column, 1, 2, 3, 4, 5, 6, right? So that might not be what you expect, but we'll talk about why that is here in just a second. Now let's check out the attributes, right? So go ahead and type attributes for M, and you'll see you get this dim attribute. And dim stands for dimensions, right? And that has 2 values, 3 and 2. So this is a integer vector that has 3 and 2. So this means this matrix has 3 rows and 2 columns, right? We can modify those attributes directly through this and get a different result. Okay, so let's change it to a 2 by 3 matrix instead of a 3 by 2. You go ahead and try first. See if you can do this without looking at the slides ahead, ideally. Give me a thumbs up if you're ready. Okay, so here we go. All I'm going to do is extract those dimensions, ATTRM dim, right? And then I'm going to redefine them with a different integer vector that's just 2 and 3 instead of 3 and 2. And then I get this. Now, this is maybe not what you would expect, right? Because if we look back at this one, we see 1, 2, 3, 4, 5, 6. If we say that we're going to change it to a 2 by 3, we might expect basically the transpose of that matrix. That's not what we get, right? We get actually a completely different matrix that goes 1, 2, 3, 4, 5, 6. Okay? So the reason is because the matrix is actually just a vector with a dimension attribute. Okay? And so here, and you can follow along with this as well, we're creating a new vector that's just 1 to 6, right? And then I'm saying, give me the dimension attribute, which it doesn't have. And I'm defining it. So I'm creating a new attribute for it called dim. And I'm setting it to 3 and 2. And now I get this same matrix we had before. All right. The filling by column probably makes a little more sense now, at least it does to me, because we have this vector and it's saying, oh, okay, I'm going to go 3 rows, so it's just taking the first 3 values and then the next 3 values, right? So that's why it fills by column, and then yeah, that's why it fills by column. Okay, so now this V, which started out as a vector, ends up being a matrix, and we got that just by adding a dimension attribute, right? As an aside, what if we wanted to fill by row? Well, if we're using the matrix function, all we have to do is say by row equals true, and then it'll fill by row, which generally is a little bit more natural to me, I think, when I'm creating matrices. But we could also do this by hand, by first creating basically the opposite of what we want, right? So we have our vector, and then we create a 2 by 4. And then, so that's what this matrix would look like. And then we just take the transpose of that vector, which is actually a matrix. Okay, so that's a total aside. It's not really important, but it shows you sort of how they get it to fill by row. They're still having it fill by column, but they're just doing they're filling by column with the transpose of the matrix you actually want. So they flip the dimensions, and then they flip them back at the end. Okay. Names. Okay, so this slide and the next are equivalent in terms of this, but we have dim, right, previously, just dim. That's the actual dimensions of the object. Dim names is going to give us row names and column names, okay? And so here I'm passing it a list, and the first argument of the list is just a vector, where a character vector that is going to be the row names for that matrix, and the second character vector is going to be the column names. Okay, so that's pretty straightforward, and now our matrix has more attributes. It has a dim attribute, dimensions, and it has a dim names attribute. Okay, we could also create this like this, right? So this is creating the whole thing. V2 is 1 through 6. We're going to set the dimensions of V2 at 3 by 2, 3 rows, 2 columns. Then instead of doing this, we just explicitly say row names of V2 is this, and the column names of V2 is this. Okay, this is, I think, more straightforward. This is how I tend to do it, but you may see people do this sort of thing fairly frequently. I think there's also a dim names function too. All right, and then V2 ends up looking the exact same. Okay, and then the other thing that I mentioned previously is arbitrary metadata, right? So I don't use this very often. Occasionally there's a use case that I think makes sense, but generally I think it's fairly dangerous, right? Because of what I mentioned before, where the attributes can be stripped. You can lose the information from there. So here though, I have my object V, right? And I'm going to create a new attribute for that matrix, which I'm calling matrix mean, okay? And then all that is just the mean of the matrix, right? Mean V. And so then when I print this out, I get my matrix up here, but then it also prints, oh, and it has this additional attribute called matrix mean, which is 3.5, okay? And then we can access that value directly rather than just having it printed to the screen, the same way we would have done it previously. Okay, you can store anything as an attribute, including other matrices or other data frames or whatever, right? It can be anything. This is a real example from multi-level modeling. And if you're not familiar with multi-level models, that's totally fine. That's not why I'm showing you this. I just want to show you basically a real applied example, right? So here's LME4, and we're fitting a model where reaction time is modeled by an intercept plus this days, which is days without sleep. It's kind of a messed up study, really. But and then the intercept and the slope for days are both random, right, by subject. So that means that there's an estimated variance in the intercept between people, and there's an estimated variance in days between people, so the slope of that days, and as well as the covariance between them. So if I use LME4 and I say var core, variance correlation, whatever, for M, and give me the subject one, right here, then this is the matrix that I get back, right? This is the variance covariance matrix for this model. And that's really useful, right? But it also gives me additional information through attributes, okay, through arbitrary metadata. So down here I have stdev, right? So basically these are the variances and these are the standard deviations, right? So just these transformed. So that's nice additional information to have. And then additionally, it gives me the correlation matrix. So this covariance might be hard to interpret on its own, but you can look at it down here and see what that correlation is, right? So this is useful additional information that comes with the varchor function, even though the actual object itself is only this variance covariance matrix. Does that make sense? So if I were to say pass that object to another function, the only thing that would actually go with it is this variance covariance matrix, not the correlation matrix or the standard deviations. Matrices versus data frames. We talked about this a little bit earlier, but the main sort of distinguishing factor between a matrix and a data frame is that all the elements of a matrix must be of the same type. And that's because, as we've just seen, right, a matrix is just an atomic vector with a dimension attribute. But one of the sort of side effects of this that's really nice is that because it's basically just an atomic vector, you can compute on that entire matrix with just a single command, right? So here I have a big matrix, right? Well, not that big, but 100 rows with a mean of 200 and a standard deviation of 10, right? And 10 columns. Okay, so it's a fairly large matrix. And I can use sum of M to sum all of the values of the matrix all at once, right? In a single operation. Mean of M, same way. And then there's additional functions like these, row sums and col sums, that will give you the row and the column sums. There's also row means, things like that, okay? And you can also do operations like this, where I'm creating a new matrix called Z, where I'm saying M, so the M like value, the element of each element of M, we're gonna subtract the mean from each element and divide by the standard deviation, right? So this is computing the entire mean of the matrix and computing the entire standard deviation of the matrix, and then computing those operations, right? So then we get a new matrix that looks like this, which will, of course, have a standard deviation, or a mean of 0 and a standard deviation of 1, okay? So this can lead to huge gains in efficiency if your data will allow it, right? If your data will allow you to work in matrices versus data frames, it can lead to huge gains in performance, okay? All right, stripping attributes. I've mentioned this a couple of times, that many operations will strip attributes. So that's why I think it's generally not a good idea to keep them or to store things in as attributes. So this is just a simple example where we have V, and then I compute the row sums of V. Notice it keeps the row names, right? But the dimension attribute is gone, and the matrix mean is gone, right? And so I mentioned that the dimension attribute is gone because that could be surprising, right? If you're looking for the row sums, you might expect to get a matrix back that is one column with the sum for each row, right? That's not what you get back. You get back just an atomic vector, okay? So if we look at attributes of row sums V, the only thing that we end up with is the names, okay? And those names are actually, so it basically took what was the row names and assigned them as the names for the new vector, okay? Sometimes the dimension is maintained, sometimes it's not. In this case, it's not. generally most things are stripped as your computing operation. Okay. I want to pause just for a second. Are there questions on any of this? Is this making sense? This is not like the most fun lecture. It's a lot of technical, dry stuff. We'll get to more fun stuff later. But I do think that this is important as like a prerequisite sort of thing as we start to think about building up loops and functions and things, because again, it's like unexpected output. And when you run into errors, being able to dig into something and understand why you're getting the output that you are is really helpful, right? So that's why we're spending so much time on this. Okay, more on names. So if we say, if we go back to V, right, which is this thing, it has index and value, and it has the first, second, and 3, right? But if I call names on V, it says null, right? And that's because I'm working with a matrix, and so it actually doesn't have names at this point. It has column names, and row names, all right? So what I can do is I can say, okay, well, let's put some names on this. I say names V is letters 1 to 6, right? So that's just going to be A, B, C, D, whatever. And then when I look at V, it's going to look basically the same, but now we have, in addition to the matrix mean, we have this names attribute, okay? So names is associated with the elements of the vector, okay? Or of the object. So names is, we have basically a vector V 1 to 6, right? And when I call names, I'm saying name each element of that. So 1, the name of the first element is A, which happens to be 1. The name of the 5th element is E, right? Etc. A little more straightforward, we could also do it like this, right? So you've seen this a bunch of times, right? Where you're creating a vector like this, but then on each element of the vector, you're saying like A is 5, B is 7, C is 12, etc., right? What this is doing is it's giving these names, okay? So V3A looks like this, and when I say what are the names of V3A, it's going to say ABC, okay? So one area where we've seen this for sure is in joins, right? If you're using like a left join and then maybe the names of the columns that you're joining on don't match, right? You would say C and then have a character vector where it's like whatever, stu.id is equal to stu_id, right? And so what that's actually doing is creating a vector, a character vector, where the name is the left data set and the value is the right data set. Does that make sense? So again, we can look at the attributes of V3A and we see we get names. Okay, alternatively, we can also do it like this. Okay, here's 2 other alternatives. So V3B, I'm creating a new integer vector here, 5, 7, and 12. And then names of V3B is equal to this character vector, ABC. Okay, we end up with the same thing. And then finally, set names for this vector. Here's the vector and set the names as this. Okay, all 3 of those are equivalent. Again, though, names is not the same thing as call names. And somewhat confusingly, both work for a data frame. I would encourage you, though, to use names, not call names, because names is actually more correct, essentially. Names is what it's actually modifying, not the call names, right? Call names on a data frame just basically points to names, and it uses names to name them. Okay, so I'll tell you more about that here in just a little bit. Okay, so why might we name the individual elements of a vector or a matrix? Well, because then it helps with subsetting, right? So here's V, and if I say V brackets B in quotes, then it will give me the element that has that name, okay? VE, get 5. Does that make sense? Okay. This is, again, how other data types are built. So quickly, we can create a factor like this, right? We would say factor AABC. And then when we say type of for factor, for fact, we get integer. Okay, and I talked about this at the end of class last time, but this can be really confusing. It can lead you to all sorts of confusion in terms of like why things end up the way that they are. Factors are just confusing generally, I think. But the reason is because all it is an integer atomic vector that has these attributes, okay? So it has a levels attribute, ABC, and it has a class attribute, which is factor, okay? If I look at the structure of fact, we see it's a factor with 3 levels. Those levels are A, B, and C, okay? Then we get a colon, and it gives us the first couple of values from that vector. Notice those values are the integers, okay? So the levels are associated with the integers in the order that they're shown on the levels. So this is associated with integer 1, this is associated with integer 2, and this is associated with integer 3. Okay, we can do this more manually without using the factor code like this, right? So first we create an integer vector, which I'm saying is 1, 1, 2, 3, 1, 3, okay? Then I'm gonna assign it some levels. So I'm saying attributes of integers, create a levels attribute, okay? Then there's only 3 integers, 1, 2, 3, right? But 1 is repeated 3 times, 2 once, and 3 twice. But I'm going to say those levels are red, green, and blue. Then finally, I'm going to change int to be a factor, the class of it to be a factor, okay? And then when I print int, we get red, red, green, blue, red, blue. So those integers are being shown as the levels rather than their integer value. And it tells us below that the levels are red, green, and blue. Okay, questions on that? Does this make sense? So if we call as.numeric on int, or as.integer, or as.double, we would get back these numbers, okay? If we call as.character on int, we would get back the levels, okay? We would get back a character vector. Okay, dates are similarly a little bit complicated, and there's dates and date times. I'm not going to talk about date times, just dates, all right? But here is an example where I say date is equal to sys.date, which is going to be today, because I rendered the slides today. And then if you say type of for date, it says it's of type double, okay? And that's because it has this, it's not going to show up like that, right? It shows up as we've seen before, like, you know, 2021-03-31, right? But that's because it has this date class, okay? And if we strip that by just saying attributes of date is defined as null, then we get this number, 18,717, okay? That number represents the days passed, the number of days passed since January 1st, 1970, which is the Unix epoch, all right? So that's like weird, but it's just a standard that people created a long time ago, and that's how dates work now. So if you had a date that was 1902 or whatever, it would just be a negative number, and it would be the number of days before 1970, January 1st, 1970. Okay, and the thing that's kind of interesting about this is not just an R thing. That's how dates are implemented across basically all programming languages, is that date, and it's a numeric value related to that date. Okay. All right, missing values. Generally, you've probably run into this before, but missing values generally breed more missing values, which is unfortunate, right? So if I say, is NA greater than 5, I get back NA, because it has no idea if NA is greater than 5 or not. So the only thing it can return is, I don't know, right? Missing values. Same thing if we try to do a multiplication with NA. NA times 7, we get NA. There's no way to compute that calculation, so we just get a missing value in return. But what about this one? What would you expect to get with that? This is sort of tricky. If you're saying, is NA the same thing as NA, then you might expect it to be true. But actually we get NA. Okay. And this is where missing values become more tricky. These two are kind of make sense, right? But this one maybe doesn't. And the reason is because if you don't know what the value is, then you don't know what the value is. So let's say you have two values and you don't know which either of them are, and then you're asking, are they equal to each other? Well, you don't know, right? You don't know if one missing value is equal to a different missing value. It might be, it might not be. So it's not saying missing is equal to missing. It's really trying to test, is the value for a missing thing the same as the value for a different missing thing? And it doesn't know. So it just returns NA. Does that make sense? Questions? Okay, so I've already said that. There's also cases where missing values don't propagate, all right? So here's an example where I have NA or true. And it returns true because when we're doing a test like this with an or, right? Or is going to return true anytime any of them are true, right? So it doesn't matter if it doesn't know the one NA, it's got one true, and you're testing if this one is true or this one is true. And so it doesn't know on this one, but it knows this one's true, so it's going to return true. Okay? If I said NA and true, then we would get NA in return, because it wouldn't be able to test if they were both true. It would say, I don't know, right? Here's another example where I have NA3, NA5, and I'm saying if I just did this inner part, x greater than 4, it would return NA false, NA true. Okay? But I'm calling any on this, and there's one true in that vector, so it's returning true. Because I'm asking if any of them are true. And so even though it's got two NAs, it can return true because there is one that is true. Okay? How do we test for missing this? Well, we've already seen that this doesn't work, right? Is x equal to NA? It just returns NA every time. Okay, and that's like a super common problem. So instead we use this is.NA function, and we get true, false, true, false. Okay, so this regularly comes into play when you have missing data in columns. And so this is a little bit older question because there's now different ways to handle this, but we used to use is.NA a lot in filtering, right? So you would filter your data frame to say not is.NA or whatever, which you could still do, but very often now we use like drop NA or whatever, functions like that. Okay, before we move on to lists, I just want to pause for a second and see how we're doing. Do people have questions on anything we've covered so far? All right. I know this again.
I've got a question actually, but how does the is.NA work in the background if we can't do the equals?
Yeah, I don't know. I have not actually really ever dug into it. I'll have to look at the source code for it, I guess. Yeah, it's got to be some sort. So there's a bunch of different types of NA as well. There's like NA underscore character, NA underscore real, which is confusing because it should be double, and things like that. So my guess is it's probably just some internal function that is able to actually detect if it's NA versus, because a lot of the base functions like that are like, even like mean and stuff are actually they're called primitive functions, and they're actually pretty much the entire code is outsourced to C. So it's all actually C code. The R is just like pulling from, essentially. So it's probably something related to that, but I'm not 100% sure. Any other questions? Okay. All right, so we're going to move on to lists now, which is kind of an entirely different topic. And again, like, I know this stuff that we've just covered is pretty technical, and it's not like stuff that I would expect that, you know, after this one lecture, you're going to be totally fluent with it. But you have it now as a reference, and it sort of hopefully will get your mind thinking in that way in terms of how things can be stored, why you might end up with certain errors, etc. Okay, and just sort of how objects in R are created generally. Okay, so lists are vectors, but they're not atomic vectors. Okay, so the fundamental difference between lists and atomic vectors is that each element in a list can be a different type. Okay, so we're not forced to having everything be of the same type, right? So here I have a list that I've created that has A, 7L, 3.25, and true. So we've got all 4 types here, and it stores them all, and we have no problem. It prints a little differently, and that's maybe a little weird, but it is a vector now that has those 4 things, and all is good, right? We didn't lose any information. So each element in a list is a vector, usually, well, always, of some type. It's possibly an atomic vector, possibly not. It could actually be a data frame, right? It could be anything. So you can store anything in a list element, okay? So the prior example on the previous slide, right here, is an example where we have 4 atomic vectors, but they're just all of length 1, right? So those are scalar vectors, basically, right? Lists do not require all the elements to be of the same length, though. So here's another example where I have L, and we've got a character vector of length 3, a vector of type double that's of length 5, integer vector of length 2, and a logical vector of length 4. Okay, and again, it stores all of that without any problem. We can check out the lists. We can say type of L. It tells us it's a list. That's cool. What are the attributes? Well, it doesn't have any attributes. We haven't defined anything. It's just a list. Okay. We can use str to give us the structure of the list, and it'll give us a little bit of a summary, right? So it's a list of length 4, and the first is a character vector, second is numeric, and then integer, and then logical. Okay. And then it'll show us the first couple of values. If there's more than like 10 values, I think it cuts it short. Data frames are actually just lists. They're a special type of list that have a data frame class, and they have to have, each element of the list has to be of the same length. Okay, but that's how data frames are created. They're just a list in the background that have this data frame class, and then each column, so each column has to be the same type, right? We can't mix character and double within a data frame column unless we have a list column. But each column can be of a different type. So here's a really quick, easy example. We have a list LDF that has these 4 different types. I've named them A, B, C, D, right? LDF is a list, but if I just say data.frame on LDF, I get this list, okay? Subsetting lists is a little bit more tricky because there's sort of multiple layers that you have to think about here, okay? So here's a nested list, and if you want, you can follow along on this part too. One of the things I've done with the slides is created this copy code thing here. So you should just be able to click that and then come over to R and paste it in, and then that way you can follow along quicker. So if you want to do that, go ahead. And then when we're subsetting the list, there are basically 3 different methods, and they're going to give you different things, okay? The $ and the double brackets are going to be equivalent. Those are going to give you the same thing, but the $ can only be used if the element of the list is named. So if it has names, you can use the $. Otherwise, you have to use the double brackets, okay? The single brackets will give you a list in return. So it's going to subset the list, right? The double brackets will give you the element from the list, which could be the vector, okay? So this is where it gets really confusing very often, right? Looking back here, X is this vector, right? The first element is just X, okay? So if I use L single bracket 1, I'll get the first element of the list in return. But now this is still a list, right? It's giving me, I'm subsetting the list, so I'm getting the first element of the list. If instead, so you can see type of L1 is list. If instead I want the contents from that first element, then I use the double brackets. And you can see that's giving me the actual vector in return, okay? So I'm getting, when I do this, you can see type of is double. It's not a list, okay? And this is something that you will get better with over time, but it's really, really important, and you will be doing it a lot. So unlike the previous stuff where it's maybe not the most important, but it's good background information, this is something that you'll need to become comfortable with, okay? Once we get that object in return, we can go ahead and subset that as well if we want by just adding more brackets, okay? So L double bracket 1 gives me this vector, and then I can subset that vector to say, give me C from that, and I get just 7 in return, okay? Because this list happens to be a named list, right? Everything has names, X, X2, X3. X3 is the list, but even that has names, vect, squared, and cubed, right? Everything is named in this list. Because of that, I can use the $, okay? So L $X2. Notice this is often how we're subsetting data frames, right? And that's because the data frame is just a list. And the column names are the names of the elements of the lists, okay? So L $X2 gives me the second, it gives me the contents from the second element, from the X2 element, right? Which is the second one. L $X3 gives me back that entire list. So back here again, L is my list, right? If I say X3, I'm getting this list in return, okay? If we end up with a case like this, where we have a list inside of a list, and this list is also named, then we can just add an additional $. So here I'm saying L $X3 squared, and now I'm getting the squared vector back, okay? This only works, though, on list elements. It doesn't work on atomic vectors, even if they're named, okay? So this is a named atomic vector here, ABC, but I can't do L X3 squared B. And I get exactly the error that you might expect, right? The $ operator is invalid for atomic vectors. So we can't use the $ operator on atomic vectors, but we can on lists, okay? So if we wanted to do something like that, because it's named, we could just do something like this. L $X3, $ squared, and then in brackets, B. Okay, and that gets us what we want. Alternatives, we can also use logical or indexing to subset vectors, or well, any vector, but including lists, okay? So here I have L, and I'm saying, I'm giving it a logical vector here, and that is true, false, true, okay? So this is going to give me the first and third elements of that list, okay? I am using the single brackets here, so it's going to return, I'm subsetting the list itself. I'm not grabbing the contents from the list, okay? So it's giving me X, which is the first element of the list, and X3, which is the third element of the list, and X3 is itself a list, so I get that list as well. Make sense? So this is a list that has two, it's of length 2, and it has X and X3 in it. I can do the same thing this way, okay? Now, again, this is getting complicated because you might say, well, I actually want the contents from those things. So you might try something like this. I'll double bracket, true, false, true. That doesn't work, right? Because it's trying to go into each element of the list, and when there's like no way to do that, right? So again, the double brackets versus the single brackets is just whether you're wanting to subset the list or you're trying to grab the contents of the list. Does that make sense? Questions on that? Okay, this is, you can look at lab 1, it's posted already, but this is going to be like the first part of lab 1 is subsetting lists, pulling things out of lists, especially nested lists, okay? Subsetting in multiple dimensions, so you're probably familiar with this, but just to make sure, generally we deal with 2-dimensional data, but we could have more dimensions. The way that we always do this is just by separating what we want from each dimension with a comma. So here's empty cars. If I said empty cars 3, 4, that's going to give me the observation from the 3rd row and the 4th column. Okay, so 1, 2, 3, 1, 2, 3, 4, 93. Okay, so it's giving me this one. All right. Empty indicators mean all. So if I say empty cars, empty, comma 4, that's going to say all rows for the 4th column. Okay, and here's same thing, the 4th row for all columns. Okay. By default, these both drop the dimensions. Okay, and this is confusing and can lead to errors and actually changes depending on if you have a tibble or a data frame. And the tibble version, I think, is much preferred, but we'll talk about that in just a second. But what we're getting back here when I use empty 4 is just an atomic vector, okay? So if I'm saying, give me the 4th column of the data frame, you might expect to get a data frame in return that has the 4th column, only the 4th column, but that's not what you get, right? You get an atomic vector. Same thing here. Okay, this is just a named atomic vector. Okay, so but this is also not consistent, because if I say, all right, here's empty cars, give me the 4th row and these 2 columns, then we'll get back, actually, I'm not 100% sure if that is an atomic vector or a data frame. We could do type of on that, I suppose. Let me do it real quick. I don't have R open, so give me just a second. So that is a list. Okay, so that's a data frame. That's what I thought. Okay, so this is returning a data frame now instead of an atomic vector. And this is just a second way of doing it. These are both the same, right? So here I'm saying the 4th column and these, or the 4th row and these 2 columns. Here I'm saying, give me all of the columns for the 4th row, and then subset that vector to give me just these 2 columns. Okay? Which actually that might not be equivalent, because that might be a vector then. Let me just double check here. Nope, it's a list. Okay. So those two are equivalent. So if instead we want to return a data frame and we want to be sure that we're returning a data frame, then we can specify drop equals false. Okay, so here's empty cars 4, right? I just get the atomic vector in return. If instead I want the data frame, you can put another comma after this 4 and say drop equals false, and then you'll get the subset of the data frame in return. Okay, as I mentioned, that is the default for a tibble. So if you have a tibble and you say, give me the 4th column like that, you will get a subset of the data frame, not an atomic vector in return. Okay, but you can override that by doing drop equals true. Okay, my recommendation if you're doing this sort of subsetting in a function is to just be explicit with this and say drop equals true or drop equals false, depending on what you want, because then it's not going to matter if the input is a tibble or a data frame. Okay, unless you've already done something so you can assume, so you know for certain whether the input coming in is a data frame or a tibble. But I have run into bugs because of exactly this before in functions. All right, basically wrapping up here, if we have more than 2 dimensions, this is not super common in the work that I do anyway, but might be for you depending on what you're doing. You can create an array that has n dimensions. It could have 3 dimensions or 4 dimensions or 5 dimensions or 6 dimensions. Outside of 3 dimensions, it gets kind of difficult for me to wrap my head around, but here's an example of an array that's basically stacked matrices, right? That's the way I like to think about it anyway. So if I have 1 to 12 and I say the dimensions of the array are 2 by 3 by 2, right? Then that's going to say 2 matrices stacked on top of each other, each of which are 2 by 3, essentially, right? So then this is the contents of the array. And then we can subset it the same way that we would before. So get just the second matrix, comma, comma, 2, right? Select the first column of each matrix, comma, 1, comma, right, etc. Okay, so that's, this is just basically an extension of the same sort of subsetting. So the last thing, why are lists so useful? I think it's fairly obvious, but the main reason is just that they're incredibly flexible, right? They're super flexible, far more so than an atomic vector. You can fill the contents with anything that you want, and from there, you can feed that to other functions or whatever. I would not recommend having a list be the output of a function that somebody else is going to use, just because lists tend to be less familiar to people. So instead, try to make the output like a data frame, right? But that doesn't mean that you're not storing everything in a list, right? So most of you, I think, have worked with linear modeling in R. If we say LM and we have something like this, what's returned is actually a list, right? It's a list of length 12, and it has a bunch of different stuff in it. But when we call summary or we call coef or whatever, anything that we call on M, it's accessing the elements of this list to create that summary, right? So that's what's happening. And this is super common. Almost any sort of model fitting that you're doing, the output is actually going to be a list, okay? So final summary here, atomic vectors have to all be of the same type. And if they're not, then you're going to get implicit coercion, right? Atomic vectors also, I don't have this in here, but I should, are the building blocks for all sorts of other complex types, right? And that's usually with an attribute tied to the atomic vector. Lists are also vectors, but they're not atomic vectors. And each element can be of a different type, of a different length, etc. And they're super flexible because, again, you can have an element of the list be an entire data frame. And in fact, that's very regularly the case, okay? So we don't have any time left, but if you'd like to practice on your own, here's another example, right? So we have this M, which is this is just the same model that was on the previous code or previous slide. even if you aren't comfortable with the modeling, that doesn't matter. If you want to practice subsetting with lists, I would suggest fitting this model and then trying to pull these things out of it. Okay, so there is a data frame in this list, which is the data that was used in the estimation of the model. So for example, empty cars, right, has many other columns, but I'm only using 2 columns here. And there is a data frame in that list that's just those 2 columns, MPG and HP. Okay, and so by using str, we can see the structure of the list, and then you can use the $ to get at these named elements. If they're not named, you might need to use attr to extract the attributes of them, etc. Okay, so that's extra practice if you want. You can also look at the lab. You could even get started on the lab if you want, which is next week. And you'll have to do some of that sort of stuff for the lab. Okay, so next time we will talk about loops with base R, and then from there we'll have the lab next Wednesday, and then we'll start to jump into different types of loops with per. Okay.